So as I said, we're going to look at some additional linear approximation problems, but what I want to do here is go back to this graph here that we talked about in the previous video and look at 1.1 here, and we could see that the error, we actually were fairly close as far as an approximation, but we should look at if I were to go further out here, and like if I were to try and approximate a value over here, for instance, and we'll do that in a second, we can see that this line, if I continue it on, this would be my linear approximation, and the error is just going to keep getting worse. So unless I'm really close to that center, that value A, the error might be unacceptable. So let's give an example of that. So let's find the linear approximation of the square root of 2 using a equals 0. Okay, so we're still using f at x equaling square root of x, so my f prime is still 1 over 2 square root of x, and since I'm using, I didn't say a equals 0, I meant to say a equals 1. We're going to use the same center. And so f at 1 is still 1, and then f prime at 1 is still 1/2. But in this case now, we have L at 2. This is going to be f at a, which is 1, plus 1/2 times 2 minus 1, x minus a, because my x this time is 2. So my linear approximation at 2 is 1 plus 1/2 times 1, which is 1.5. So what we're saying now is that the square root of 2 is approximately 1.5. And then if I do, I'm sorry, I stopped talking here for a second, but I'm just typing this into my calculator here. If we do it in a calculator, the square root of 2 is actually equal to 1.41421 going on forever. So we can see right away that this is not nearly as good of an approximation, because even if you round it to 1 decimal point, so if we round it to 1 decimal point, the actual answer for square root of 2 is 1.4, and we're saying it's 1.5. And that, again, if we go back to this figure, that's because I'm getting further and further away from this center value. Now there is a way to correct for that, and that is something though that you'll learn in Calc 2, because we can do more than just a linear approximation. We could do a quadratic approximation, we could do then a cubic approximation, so on and so on, and that leads to something called power series, which is well beyond the scope of Calc 1. Right now we're just focusing on linear approximation. Now, let's look at another one here, and this one actually is very widely used here. Find a linear approximation for e to the x using a equals 0. Alright, so my linear approximation, so I'm just asked to find this equation, L at x. Well, the linear approximation, remember, is f at a plus f prime at a times x minus a. And so what we get here is we get, well, f at x is equal to e to the x. F prime at x, of course, is still just e to the x. and then f at 0, my pen is still misbehaving for me, f at 0 would be e to the 0, which of course is 1. F prime at 0 would be e to the 0, which is also 1. And so my linear approximation would be f at a, which is 1, plus f prime at a, which is 1, times x minus a, and in this case a is 0. So my linear approximation here is equal to 1 plus x. So what are we saying here? What we're saying is that e to the x is actually approximately 1 plus x for x near 0. Because it's always going to be near your center. And this result here, believe it or not, this result is incredibly useful. We actually use it in engineering quite a bit to get a handle on some things. It also is a way to solve equations with e to the x if you know your answer is close to 0. So this is actually a very important linear approximation. But I'd like to look at one more linear approximation, because the square root of x is great, but that doesn't always show up on the exam. And when we get a different function, sometimes people really get just completely confused and really go off the deep end here. And this problem really shouldn't be difficult. So let's do this here using a linear approximation. With a equals 0, approximate the cosine of 0.1. And we'll do the cosine of 0.1, and then we might do one more here. Now this one is going to be a little bizarre for us here. And actually, I'm going to change that. Instead of doing cosine, I want to do sine. Sine of 0.1. So we're going to do a linear approximation here. So first off, we need to figure out what my function is. Well, the function that I'm approximating, of course, is the sine function, sine of x. So with my linear approximation, I'm going to write the equation down again. F at a plus f prime at a times x minus a. Well, I need the derivative. So f prime at x, well, that's easy. That's just cosine of x. And then what do I need here? I need to also know what f at a and f prime at a are. So I have f at 0, which would be the sine of 0, which is 0. F prime at 0 is the cosine of 0, which is 1. So my linear approximation, I'll just write the equation down first, is going to be f at a, which is 0, plus 1 times x minus 0. So actually my linear approximation, when I simplify this out, is just x. And so what we're saying here is that if I do a linear approximation here at 0.1, well, that's just 0.1 then. So again, what are we saying? We're saying that the sine of 0.1 is approximately 0.1, which is an interesting result. And if we want to again verify how good this approximation is, we can turn to our calculator, and if we calculate this out, the sine of 0.1 is actually equal to 0.0998 9, 9. Man, my pen is really acting weird this morning. 9, 9, 8, 3, 3, 4, dot, dot, dot. Which again, if you round this, it would round to 0.1. So it's actually not a bad linear approximation. Of course, the further away we get from 0, the worse the approximation would be. So this kind of marks the end of linear approximation here. You can be guaranteed that there's going to be one question on your exam that deals with linear approximation. Now, we still have another topic to discuss in this section called differentials, and we'll do that in the next video.